Okay, so let's look at example 6. You are having a phase diagram of silver and PT with percentage of silver. The more you you walk to the right, you have more silver. And then on the top, you have liquid. On the bottom, you have a solid alpha plus beta. On the left, you have gamma alpha. On the right, you have beta. Okay. And from this graph, you already know where is the paritetic point. Okay. So we slowly see what the question wants us to do. So we make phase analysis. We are given a point, a new point at 42.4% Ag and new temperature 1400. So you go to the diagram, right? Go to diagram, pick the percentage of Ag, 42.2. You draw a line with this alloy 1 in this example, and then temperature at 1400 Celsius. To this one. Okay. So for phase diagram, always identify where is the composition and then where is the temperature. So here, you also drop down what is on the left. Do the same as your euthetic steps. You look what you have on the left, what you have on the right. So here, you drop down on your left, you get about like 7%. But 7% of what? 7% of alpha. Then on the far right here, this point, right? This point, you get 55. 55 of what? Liquid. Okay, so know your left pocket, right pocket. And then the center is the one that given in the question, 42.4%. So first person, you have alpha liquid. Then composition of the phrase, you read from the graph. Alpha, you have 7% of alpha. What kind of alpha? You have Ag in alpha because you have binary system. It can be PT alpha, it can be Ag alpha, right? So in here, we have Ag alpha. Then you have 55% Ag here in liquid. Do the same amount of phrases. Also pick the total length is here to here. 55 minus 7 is the total length. Then the one that near to the left-hand side of alpha is the opposite one, right? So to calculate the alpha, you pick the another side here to here. So 55 minus 42.4 divided by total length times 100, you get the amount of phrases for alpha. Okay, do the same for liquid, same, right? Or you just take 100% minus 26. Okay, point B, repeat the same process. Now point B, 42.4% still the same, but the temperature change, 1186 is the paritetic temperature, but just above the paritetic temperature. Okay, where is it? It's just above, just above this one, just above. So on the left, just above, it means you have alpha, a bit of liquid and alpha, and also liquid, full liquid. Right? So read from the graph, you have the composition of both ends. Right? First person, you read from the graph, liquid and alpha, or alpha liquid, same, right? Then composition, read from the graph, amount of phrases, do the same calculation, get the 3 point, and then you get the ratio. Still the same, nothing complex here, still the same. What is the challenging part is to identify where is your paritetic line. Okay, we're still using level rules to solve. Okay. Then C is minus delta from paritetic. It's just below the line. Still the same, but it's just a little bit below. So a little bit below, here, paritetic line, 42%. Of course, this graph is very hard to see whether it is only beta, because this is very, very small, very, very small. It's very hard to see. Yeah? So if you enlarge the graph, then you will see you will have you it will meet the this blue line that tell you is beta. Okay. Section C is not fair for you because the graph is very small. But this is how you do it lah. You read from the graph. Okay. Of course, assessment we won't ask the area that very questionable like this. Okay. Point D on 60%, 115, repeat the same, go to the 60%, draw the temperature line. Okay, 60% is the one alloy 2, 1150 around the red line that I draw. So within this line, okay, within this line, where did you look for? What are the points you look for? You go to the percentage of that. For example, this one is 60%. Then you draw a horizontal line. You focus on the one that very near to the perpendicular line. In here, you see it's like 48% and 77%. You don't look for the other. So you draw a vertical line of the percentage, weight percentage. Then you draw a horizontal line. You only concern that what is on the next point of your horizontal line from the interest point. This one touch here, so you read the value. From the 60%, you go to the far right, touch this point, you drop down. Okay. So you have liquid and beta. Okay. Okay, now here is also very unfair to you because it's very hard to read. This line, this blue line, it can be alpha and beta, but alpha, beta, the more you go to on top of this blue line, it becomes beta, right? Yeah, it is quite a challenging part to see, but the procedure still same. Okay, this one you read from the slides. Procedure still same. Again, assessment, we won't ask you the very, very narrow area. We'll ask you some very big area. Okay, the next terms that we learn after the break, we introduce you a term called monothetic. Monothetic is a liquid phase transformed into solid phase or other liquid phase. The equation will be this one. So we have introduced what is eutectic, what is paritetic. Now you introduce another one, is called monothetic. Monothetic, liquid left-hand side, equation on the right-hand side will be alpha plus liquid. Liquid of another one, liquid L2. So you have alpha solution plus liquid solution on the right-hand side of the equation. Okay, so you see paritetic is liquid plus alpha solution. You get beta solution. You compare side by side is actually quite different. Eutectic, liquid become alpha beta, but mono, how you memorize? Mono means you only get one. Mono is one. So one solid inside the product. So you only get alpha, right? Alpha solid in the final product. Okay. Now, this is the phase diagram that introduce you how to identify monothetic. So on this graph, again, what is the equation of monothetic? Okay, so again, eutectic point. How you find eutectic point? Eutectic point is the last drop of liquid that you can see. So liquid, alpha liquid 2, L2 means liquid number 2, and alpha beta at the bottom. So first eutectic is the last drop of liquid. You follow the liquid line. You follow the liquid line, you drop the temperature, is the last point here. Again, it's very unfair for you because it's very, very narrow area here. So this is the last point on the graph that give you the liquid, last drop of liquid. Doesn't matter whether it's liquid 1, liquid 2. Doesn't matter. So on this graph, the last point of liquid appeared here, 327.5 something degree. Then this black color is the boundary between alpha beta and alpha plus liquid number 2. Yeah, eutectic, just recap what is definition of eutectic. So as a result, terminal solid solution or pure lead or 0.07 copper and pure copper are formed at room temperature. So this is just an illustration. Okay. Also cannot read from the graph also. It just tell you that what happened. So this is under microscope. When you have monothetic, you only see one type of the solid inside there. Okay, perithetic, you see dark color, you see gray color, and so on. But monothetic is only see one type of solid. The rest you read. Okay. So we have three type of diagram: eutectic, perithetic, monothetic. There is a shortcut table or cheat code for you to memorize. This one won't be given in the exam. This is just a cheat code or summary of what we learned. So eutectic is liquid become alpha beta, or you will see something like this: alpha left hand side, beta right inside, and then something like that. Eutectic also same. Eutectoid is another one, which we do not go deep into that. Eutectoid, if you look at this one, if you get beta plus gamma. Perithetic is what we discussed. Perithetic is alpha plus beta, you get gamma, it's called perithetic. Monothetic is like this one. So when we look at other material later, we will introduce you perithetic and eutectic. So far we cover three, eutectic, perithetic, monothetic. Okay. Right. So eutectic and eutectic reaction are similar in that two solid phase are formed from one phase on cooling. So you can see here, eutectic and eutectic, the product we have two. Eutectic is alpha beta, but eutectic is also two product, beta and gamma. Right? That is the similarity of eutectic and eutectic. Perithetic and perithetic, they are inverse of eutectic and eutectic. You see, perithetic and eutectic, you have a two product on the left before it changes to one product on the right. Actually it's a flip process of eutectic and perithetic. They are actually flip. Process is flip. Okay. All right. All right. So this is just a process, just for your information. We won't ask you this one in your test. So just introduce you how iron was made in the factory. So this is the production floor. So you can go and read when you have time. Okay. So this one you read how the carbon steel they are being made. They mix ferrum oxide plus carbon monoxide, you get ferrum and carbon dioxide. Okay. This one is sheet making, also another process. I won't ask you this one. Okay. It's a conversion from pig iron into steel. So this one is just mixed with oxygen and then you pour out, then you get the pure steel. The rest you read. It's just a chemical reaction. Okay, this is the production floor if you work in the steel industry. Okay, why we show you all this diagram? Because the next phase diagram, we're going to touch ion carbon system. Okay, ion carbon system. The first type of carbon steel is called plain carbon steel. How you differentiate from other type of carbon steel is the percentage of carbon is very, very low, and manganese is also very, very low. Roughly 1% for both. 1% roughly 1% of carbon, 1% of magnesium, right? Okay. So just take note that for this module, plain carbon steel will be treated important as iron carbon binary alloy. So we'll introduce you one new type of, not new type, but another type of phase diagram is called carbon steel diagram, or carbon steel diagram. Here, phase diagram also same. The way you read it, actually the same. Percentage of carbon means the more you walk to the right, you get more carbon, right? And so on. So in this case, you have a Fe3 carbon and then 100% ferrum. This is a ion carbide phase diagram. Again, the one that you see for the phase diagram, they are not the real one. They just simplified for theory class. And actually, they are this phase diagram for carbon steel. They actually you can follow a pattern because it's like a recipe. It's like a secret recipe for you to make steel. So the steel industry, they rarely dispose or really give you the recipe, because on this graph you can control, once you can control the temperature, you can control the percentage of the element, you can make the type of metal that you want. Okay, so right, so okay. Okay, let's jump into the graph that we will be using, or the one that you see in your coming test or final exam. So here you read the percentage of carbon here, and then the temperature. Again, the carbon percentage is very, very low because we are assuming we are using plain carbon steel. Plain carbon steel is about 1% of that one, but we push until something percent. Okay. And what are the ingredients you have? Liquid on the top. You have bottom alpha Fe3C. What is Fe3C? Fe3C is called cementite. Okay, cementite, they can decompose into more stable phase of iron and carbon. We call it graphite. Okay, so we will treat Fe3 as a stable and equivalent phase. So that's why on the phase diagram, you see Fe3C. And in more simplified diagram, you don't see Fe3C, you see carbon. So on the plain carbon steel phase diagram, Fe3C is the one that if you forget what is the name of Fe3C as a cementite, you can just write the formula. No issue for me. Means that you understand the graph. Okay. Okay. If you compare side by side, the one on the left and the one on the right actually is the same. It's only the scale. The one on the right is like more fat people. We stretch the x-axis. The one on the right graph is like you scrap, you push, you make the x-axis narrow, so you push all the lines become sharper. Yeah, they actually is the same graph. Okay. So FE3 diagram contain the following solid phase, as you can read directly from the graph. So I will not go deep, mention one by one, but I believe you know how to read graph directly. All right. So here you have four types. You have alpha, you have cementite or Fe3C, you have a delta ferrite. Yes, delta. Delta is here. Delta ferrite. You have austenite gamma here, here. Okay, so you have four types. Right. So sometimes we just want to help you to score some marks. We just ask you the first question: what are the from the phase diagram? What are the solid phase that you have? What element that they are that appeared in the solid phase in this phase diagram? So you just write all the elements that appeared in the solid. Okay. So again, alpha ferrite. We try to link back to your chapter 2 or chapter 3 when we discuss about the crystal structure. So ferrite alpha, they are in BCC or a BCC structure, right? Looking like this, right? And then, yeah, the rest is very technical. So ferrite here, okay, here. Alpha is here. So the point is very small, right? Very small. Actually, I should show you another one, the fatter, the longer one, but it just show you the area. So the alpha, there's only have a very small play margin. Maximum solubility is 0.02% of your carbon, solid solubility, and 0.005. Very small. Cannot see here. Right? So 0 degree C is here. The blue line actually extended to here is 0.0005. This graph don't show you that value. So you know that this is BCC. So BCC, if you do the analysis between the size of radius of carbon and the space that you have in BCC, actually carbon you find it's very hard to fit into this space here. Okay, so that's why you see the solubility of carbon is very low. If you reduce the temperature, your crystal structure will shrink, right? Will shrink. So it make it more difficult for the carbon to fit inside the space here. Okay, just now again, alpha is BCC structure. Gamma, austenite, or gamma, or call it gamma. Gamma have FCC crystal structure. So BCC is the alpha. Gamma, you have FCC crystal structure, which I highlight on this line here. Okay. So FCC is a phase crystal structure, which look like this. All right. Okay. So again, just show you some graphical presentation. So how you fit carbon into FCC? So you can see the space between the atom here. FCC, there's a space here. You see this atom size is quite small compared to the space you have between the FCC. How to calculate the space that you have here? Go back to chapter 2 or chapter 3 when you do the FCC analysis. We already know the A in the table. The A, you know the radius of, in this case, ferrum. Radius of ferrum, radius of ferrum. So you have a remaining space here. So then you go and find the carbon radius. So you're going to find the space whether carbon can fit in or not. So as you can see from this diagram, the size of carbon is quite small, that can fit easily. So that's why you can see on the graph here, this line here, it will push for more percentage of carbon in the gamma phrases. Okay. Right. Yeah, the rest is read from the graph. Quite direct, huh? Quite direct. Solubility maximum carbon at 211 here. And then you extend this temperature is 1173. Sorry, 1148 or 1150 here. Okay, maximum solubility. What is maximum solubility? Means maximum percentage of carbon that you can put inside the ferrum. All right, it means you want to make alloy. Want to make alloy. So if you want to make alloy in FCC stage, maximum you can go is 2.1% of carbon at 1147 degrees C, so that you can mix. This is a temperature, maximum temperature that you can go, so that you can mix the carbon and you get FCC crystal structure. Okay. Then the FEC3 cementite. We have ignorable solubility limit. Composition can have very large, from 6% to 93%. Right, very large, huh? Very large. And Fe3C basically is a carbon. So carbon is very hard and brittle. Right? Another one, delta fluoride. Delta fluoride, they are in BCC. Again, BCC is very hard to put carbon. Huh? BCC structure, it hates carbon. It don't allow carbon to fit in. But FCC is very welcoming carbon. So you just memorize that, right? So FCC, it just welcome a lot of carbon to fit in. So delta, you have BCC, so also very low. Also very low. So you see from the graph, delta on the top here. So very, very small space that can fit in, because it have BCC crystal structure. Okay. Then paritetic, again. Paritetic is what? Paritetic, liquid plus alpha, you get beta, right? So you look from this graph, where does the alpha, liquid plus alpha happen? Right? So paritetic for the carbon steel, it appeared, let's see, on the top here. So they are two, can say they are two paritetic reaction. It depends on what you focus on. Because on the graph here, you have delta, you have alpha. It depends on what kind of carbon steel you want to make. So if you drop from the top, the first paritetic reaction is because liquid of delta, you change to gamma at this section here. Okay, so it's very, very narrow area. Liquid at 0.53% carbon, very, very small. And gamma, delta, until it becomes gamma. Gamma is here. Gamma is here. Right? So very, very small area here. Very small area here. Right? Eutectic. Eutectic is the last drop of liquid that you can see as you drop temperature. So if you drop from above, liquid, you follow the liquid line, this is the eutectic point. This is the last drop of liquid that you can see at here. Okay, I think eutectic is the most direct one. Okay, so I highlight for you. So this is a eutectic point. You change liquid to gamma and carbon over here, this region. Okay. Eutectoid, you refer to the graph, the table just now. Eutectoid is gamma to alpha and so on. So this one you refer to the table and then you look carefully on the diagram. Okay. Again, forum carbon steel phase diagram is very popular for assessment. So when you do revision, this second half of the session, the slide that I show you is very important. Especially you try to identify where is eutectoid, where is eutectic, paritetic area, and so on. You make your own map so that when you come to test, you can straight away go to that point and then do analysis. Right? Okay. So the rest you read. Everything is on the slide here. So when you have a eutectoid reaction, then you get eutectoid steel. How again you have a hypo and hyper. Hypo is more than 0.77%. Less than that value, it becomes hyper. Okay. Okay, where is eutectoid? Here. On the far left, far right, hypo, less become hyper. Okay, I think we go for this example 7. Okay, then we call it a day. Okay, so you're given a carbon steel phase diagram. So 77%, 0.77% carbon, eutectoid plain carbon steel was slowly cooled from a certain temperature, in this case 750 degrees C, to a temperature slightly below 727. Assume astatite is complete transfer from a transfer to alpha, ferrite, and cementite. So you need to do calculation, weight percent for two, what percent for eutectoid and for ferrum and cementite. So you identify the area first. All right. So the question gives you a few information. Use the information, draw the lines on the graph. So you have 727. You have 0.77%, which is roughly here. All right. So as you can see, the first step always draw the vertical line from the weight percentage carbon, the target or the question percentage. You draw the line, and then you go temperature 727. Right, 727 is roughly here. 600, 727 is here. Right, it tell you just below. So I just highlight just below here, just below 727. I draw with a solid line there. So I just calculate percentage of ferrite that I have. So here I take 0.66%, 6.7% because this is the maximum graph that I have. So I take the maximum point minus 0.77 here. So you draw a line. So you have 3 points, 1, 2, 3. So you just still do the same percentage calculation. Okay, 1, 2, and 3. So percentage of ferrite, take the final point minus the center point divided by the total length. By 100, you get ferrite, which is alpha. Right? 88%, quite high. Then for cementite, what is cementite? Fe3C. Cementite is Fe3C. So cementite is this side, so you use here, or 100% minus this one. Same. Okay. You get 11.3%. Okay. Okay, then I think the rest is just explanation, just explanation. Okay, this one is extra exercise. What is your homework today is to get familiar with all these bombastic words. For example, what is eutectoid? What is cementite? Yeah, and so on. All these things. I think you are familiar with how to pinpoint the point on the phase diagram. Only you need to be familiar with technical word. For example, eutectoid, cementite. When it's gamma, alpha or gamma phase or delta phase, what does it mean? And then two type of crystal structure we keep repeating is a BCC and FCC. Okay, so this example 7, also your homework. I will not go deep because it keep repeating the same procedure. Okay, you keep repeating the same procedure, and I will. This one your homework lah. Go your homework. Go and see this example A and B how to do. Okay, still the same. Still the same. All the steps are there. Right. So again, you will see pro-eutectoid. What is that? Austenite. What is that? So go and read the PowerPoint slides. Okay. So example 7. Okay. Then next lecture we look at slow cooling plant iron steel. What are the perrite? This one is in your lab where you see perrite. And so on. So next lecture we'll introduce you what is perlite and other things. Okay, so today we stop here. Okay, so go home and see example 7. How you find point on the plain carbon steel graph.